want to start with a disclaimer that part of this talk that I'll talk about the impact of NJ West 2 on MC sub R ground motions is actually pretty short and preliminary. Proposals for new MC sub R ground motions based on the new USGS hazard model that you heard about from Mark are still underway now. So that part's going to be pretty preliminary. But I'll talk about these four things. The organizing committee for this seminar thought that since in California the 2012 IBC is becoming law in January, as I understand, that it would still be helpful to talk about how the new MC sub R, the risk-targeted MC ground motions in the 2012 IBC were derived. So I apologize to those of you here who have heard this too many times, but hopefully that's not everyone. So I'll also talk about some new USGS web tools for either obtaining or calculating MC sub R ground motions. You'll see that the derivation of MC sub R ground motions has gotten more complicated, but we're hoping with the tools that we're making it even easier for engineers to get at these values and even do some of their own calculations. All right, and then finally at the end, for a little bit, I'll get the impact of changes from NJ West 1 to NJ West 2 on MC sub R ground motions specifically. And just to put those changes in perspective, I'll show a little bit of impact of other modeling changes like the earthquake source modeling that Mark talked about on MC sub R ground motions. Okay, so let's start with the 2012 International Building Code. They have maps like this in them of spectral response acceleration, and they look very much like the maps that were in earlier editions of the International Building Code, except that now they are risk-targeted maximum considered earthquake, MC sub R, with the R being for risk-targeted ground motion maps. And we'll talk about what that means. All right. This slide is sort of serving as an acknowledgement for the long process and the many people involved in developing the MC sub R maps. So starting on the bottom here, the USGS in 2008 came up with a new hazard model and led by Mark Peterson, but it was really the Building Seismic Safety Council, Project 07, that was chaired by Charlie Kircher, that came up with a way of taking the USGS hazard model and driving from that maps that are going in ultimately into the International Building Code for design purposes. So those Project 07 maps ended up in the 2009 NEHR provisions. Then ASC 7, the 2010 version of that, made those maps into a standard, and also did a little bit to simplify the maps that were in the NEHR provisions. And then, of course, the 2012 IBC adopted the maps that are in 2010 ASC 7. So the ground motion values, the MC sub R ground motion values that you get for any of these three documents will be the same. There's a little bit of a difference in how they're presented. They're presented in a more detailed way in the NEHR, 2009 NEHR provisions versus ASC 710 or the 2012 IBC. Okay, so this is just a graphical way of looking at the derivation of the MC sub R design maps. So on your left-hand side here is the way that MCE without the sub R ground motion maps were derived for the 2009 and previous International Building Code, right? So many of you may be familiar that the basis was a uniform hazard map. So a map of ground motions that all have 2% probability of being exceeded in 50 years. So that was the main basis, but there also were deterministic ground motion caps that were applied to these 2% and 50-year uniform hazard ground motions to get at the MC sub R ground motion maps. So the process is overall pretty similar. We still have deterministic ground motion caps in getting to the 2012 MC sub R ground motion maps, but now the probabilistic part up here, it's not a uniform hazard ground motion anymore. It's a risk-targeted map, and I'll state this now, but explain it in the following slides. This risk-targeted map is a map of ground motions that are expected to give you buildings that have a uniform 1% probability of collapse of the building in 50 years. So they're associated with a risk probability now of collapse of the building instead of the uniform hazard map, which is associated with the probability that the ground motion is exceeded. Okay, so this process, this derivation of MC sub R ground motion maps is really laid out in the site-specific procedure of ASC 710, chapter 21. And essentially what that says is, there it tells you that MC sub R ground motions, they're the minimum of probabilistic ground motions and deterministic ground motions, where the probabilistic ground motions now for the 2010 ASC 7 standard are risk-targeted probabilistic ground motions and calculated according to method 2 in the site-specific procedure. There's also a method 1, which is essentially just a method for approximating risk-targeted ground motions. And then also the deterministic ground motion part of MC sub R ground motions, there are 84th percentile ground motions, 84th percentile from characteristic earthquakes, and if you're at a particular site, it's really the 84th percentile from the characteristic earthquake that gives you the biggest ground motion. But there's also some floor to these deterministic ground motions that I'll go over this in more detail later. Right, so these are the basic components, though, as laid out in the site-specific procedure. There it also lays out that now all the ground motions are maximum direction spectral response accelerations. And you heard Yusuf talk about that this morning a little bit. And then really you can think of the maps in 2012 IBC as taking the USGS hazard model, applying this site-specific procedure from ASC 710, and arriving at MC sub R ground motion maps. Right? So again, kind of the same way in a site-specific analysis, you might take your own hazard analysis and follow the site-specific procedure to derive at MC sub R. We're just doing that, but we're using the USGS hazard model and putting it on a map. Okay, so for the probabilistic ground motions, to actually look at some of the text from ASC 710, and this is also in the 2009 NEHR provisions. So the probabilistic ground motion is spectral response accelerations, now in the direction of maximum horizontal response, like I just mentioned. And now there are ground motions that are expected to achieve a 1% probability of collapse within a 50-year period. Right? And so that's the part where this site-specific procedure used to say ground motions that have a 2% probability of being exceeded in 50 years. No mention of collapse risk. And then I mentioned method 2 of the site-specific procedure is what kind of lays out how you calculate these risk-targeted ground motions that achieve the 1% of 50-year probability of collapse. And that description is pretty, it's very accurate, but very brief. It's good code language, but it doesn't necessarily tell you exactly how to do this. And so hopefully the examples I'll show help with that, and also a tool that I'll show. So, but method 2 essentially says that you calculate these risk-targeted ground motions via iterative integration of a site-specific hazard curve with a log normal probability density function representing the collapse fragility, right? That's the lingo. And then the bottom 2 lines essentially define what is that collapse fragility, all right? So let's look at this a little bit closer. So bottom line is it says probabilistic ground motions are risk-targeted ground motions now. All right? So the risk-targeted ground motions, as the site-specific procedure alludes to, it's calculated iteratively, and the components are, and we'll look at bigger versions of these plots in a second, so don't worry too much about the details, but the components are ground motion hazard curves. For the mapping purposes, we're using those from the USGS hazard model, and hazard curves are something that tell you, as a function of ground motion intensity, what is here I plotted annual probability of exceeding that ground motion intensity. And I plotted that for a couple sites here. Other component are building fragility curves that were really defined by project 07. And building fragility curve again tells you, as a function of ground motion intensity, what is the probability of collapse of a building if you see conditioned on that particular ground motion intensity. And an important thing to note here is that building fragility curves, they depend on the level of ground shaking that you design for. If you design for 0.1 G versus 1 G, the 0.1 G design is going to have more fragility. Right? So that's an important thing to remember here, and this is what makes the procedure iterative, that you're trying to come up with a ground motion to design for, and yet the fragilities, they depend on that ground motion that you designed for. Right? And then the last component is a risk target, and defined by Project 07 as a probability of collapse in 1% in 50 years. And because it doesn't make sense now, and I'll probably forget later, someone can ask later how we got that 1% in 50-year number. All right. So these things are combined via something that's often referred to as a risk integral, and you can find it as far back as ATC 306, maybe even further back, but that's late 70s. And the risk integral tells you that an annualized probability of collapse of a structure can be computed via integrating the derivative of a fragility curve, right, with a hazard curve. So the fragility curve tells you if you see a particular level of ground shaking intensity, what is the probability that your building will collapse. The hazard curve goes and tells you then what are the probabilities of the different levels of ground shaking intensity. All right. Okay, so oh, sorry, let me step back for a second. So what we're doing here is we're figuring out, and since the fragilities depend on the level of ground shaking that you design for, we're trying to figure out the level of ground shaking you design for in order to get a fragility that when put together with a hazard curve for your site, give you the target risk of collapse. Right? And we'll go through an example, but that's just a brief way to state it. And here's another way to look at that process. These risk-targeted ground motion, again, it's iterative, so you start with a guess of what the risk-targeted ground motion is. Right? Then you generate a fragility curve that depends on the risk-targeted ground motion. It depends on the level of ground shaking you're designing for. Right? You take that fragility curve and you integrate it with the hazard curve, the ground motion hazard curve for your particular site. And then you're essentially calculated via the risk integral what the probability of collapse is in a 50-year time period. And if it's 1%, you guessed right. You got the risk-targeted ground motion. If not, you go and you tweak your risk-targeted ground motion, tweak the fragility curve because it depends on that risk-targeted ground motion that you're designing for, do the risk integration, and check again, right, until you've reached this goal of 1% probability of collapse in 50 years for the building design. Okay, so let's go through a specific example. So this is just showing two sites that we're going to use. One is a San Francisco Bay Area location, and one is a Memphis metropolitan area location. So first, the hazard curve component of this calculation. So again, hazard curves tell you as a function of ground motion intensity, what is here I've written it as annualized probability of exceeding that ground motion level. All right? And here we have one curve for the San Francisco Bay Area, the red one, and a blue one for the Memphis location. All right? A couple things to note. Because ASC 710 site-specific procedure has specified that we're to use max direction ground motions, and yet what the USGS produces in terms of hazard curves are really hazard curves for a geometric mean type spectral acceleration, because that's what we have for ground motion prediction equations. Per the recommendation of Project 07, we've factored the spectral accelerations on these hazard curves by a factor of 1.1 if you're looking at 0.2 second spectral acceleration, like in this example, or 1.3 if you're looking at 1 second spectral acceleration. Right? And those are approximate conversion factors. And then the other thing to remember is that a conventional 2,500 year or the 2% probability of exceedance in 50-year ground motions, they're interpolated from these types of hazard curves, right? Just like illustration here. And so an important thing to note here is that for these two examples, the 2,500-year ground motions in these examples are pretty similar for San Francisco and Memphis. But you can see for that, the rest of the hazard curves really aren't that similar. They're quite different. They have different shapes to them. And in a nutshell, what this risk-targeted approach does is consider the differences in the shapes of these of these hazard curves. It doesn't just look at one location on the hazard curve, which happened to be maybe where they intersect. It looks at practically the entire curve. Okay, so then the fragility curve part, a component of doing this risk-targeted ground motion calculator. Okay, so we start remembering that the fragility curves depend on the level of ground shaking that we designed for, this risk-targeted ground motion. They depend on that. And again, we're doing the iteration. We're going to start out saying, for the first iteration, let's just assume the risk-targeted ground motion equals the 2,500-year ground motion, which we saw on the previous slide were pretty similar for these two locations, 1.3 G for San Francisco, 1.2 G for Memphis. So we're building a fragility curve by using information from what's now FEMA P695, an ATC 63 project. And that project, in short, told us that if you design for a certain level of ground shaking, and then you actually see that level of ground shaking, that your building has roughly a 10% chance of collapsing. Right? So we're, in this first iteration, we're saying, hey, we're going to design for about these levels of ground shaking, and those are, if we see those ground level shakings, or ground shaking levels, we're going to have a 10% probability of collapse. So that gives us a point on each of the two fragility curves that we're building here. And then essentially we assume a log normal probability distribution, which is pretty common for fragility curves, and with a specified slope or standard deviation of that log normal probability distribution. And that's a value of 0.6 that's specified in the ASC 710 site-specific procedure. Okay, so with that equation and assuming a 0.6, this parameter is often referred to as beta, 0.6 beta, we get our fragility curves for these two different locations where we're starting with an assumption about what we would design a building for at each of those. And the fragility curves are pretty similar because they're saying you're designing to pretty similar levels of shaking at the two locations. All right? So those are the fragility curves that we're going to use. One thing that I'll note here, because it'll come up again later, and then if somebody is looking in the site-specific procedure or one of the new tools that I'll talk about, they'll probably come to notice this, that for the 2012 IBC, for the maps, the MCER ground motion maps that are in there, we actually used a beta, a slope or standard deviation parameter of 0.8 instead of 0.6. It's just that the maps were done with 0.8, but by the time we say, well, probably 0.6 would be a better number to use. It doesn't make a huge difference in the MCER ground motion values. And so the maps weren't changed, but it was decided to go ahead and specify the better value of 0.6 in the site-specific procedure. Okay, so we have the components. We have also our risk target, the 1% and 50-year probability of collapse, the risk integral that we're using. And here I'm just showing the hazard curves, the hazard part of the risk integral for the two locations. Right? These are the same as we saw in the 2 slides ago. And then these are the fragility curves, the same ones from the previous slide, for our first iteration, where we're assuming we would design to pretty similar levels in San Francisco versus Memphis. And then this bottom pane kind of shows the product of the hazard curve with the derivative of the fragility curve. You take the area underneath this, integrate this, and you get out, now for San Francisco, a probability of collapse in 50 years of 1.2%. For Memphis, you get a probability of collapse of 0.7% in 50 years. Now these aren't too different, they round to 1, but the question becomes, if you make these probabilities of collapse in 50 years the same for the two locations, what does that mean in terms of the ground motions that you would design for, right? Because if you leave it as now, what you can get is people in Memphis saying, if I design for uniform hazard ground motions, which is the assumption we made in this first iteration, you're essentially holding me to a higher standard. You're saying my buildings have to have less risk of collapse than buildings in this example, San Francisco, all right? And that's not fair. All right, so let's remember these values, the 1.3 and 1.2 G here, and then ending up with 1.2% and 0.7% in 50 years. we're going to go to our second iteration, where we're going to increase the ground shaking that we designed for in California to reduce that risk that we saw there. And we're going to relax the ground motion that we designed for in Memphis in order to allow the risk of collapse to go up to, we're going to try to get to 1%, right? So these are the same hazard curves. The hazard curves don't change. The hazard curves are what they are. The fragility curves now do change, because now we're in this iteration, we're saying, hey, what if we design for 1.5 G in San Francisco and 0.9 G in Memphis? And now you see that the fragilities are different. You get higher fragility, that is for a given potential ground shaking intensity that you see, you get a higher probability of collapse for the Memphis location here, where you only designed for 0.9 G. So again, you can integrate these two curves, and we find now, well, we overshot a little bit. We got 0.8% probability of collapse in 50 years in San Francisco and 1.1 in Memphis. Now it's not fair to San Francisco. So pretty quickly, this iteration doesn't take long. It's a few times, and you can come up with, what is the ground motion that I should design for? What is this risk-targeted ground motion, such that it gives me these fragility curves here that, when integrated with the hazard curves here, end up with 1% probability of collapse in 50 years in both locations. All right. And so we've ended up at about 1.4 G in San Francisco and close to 1 G in Memphis. So a little lower in Memphis, whereas uniform hazard ground motions would have told us we could do about the same, we designed for about the same level in the two locations. Okay, so we do that exercise for every location in the US, across the grid covering the US, using the USGS hazard curves, and then essentially we get a risk-targeted ground motion map, and that's targeting 1% probability of collapse in 50 years for buildings that would be designed according to that ground motion map. All right. And one thing people immediately will ask is, well, how does that compare with what we used to do, using uniform hazard ground motions, 2% in 50-year ground motions? So something was defined called the risk coefficient, which is just the ratio of the risk-targeted ground motion divided by the uniform hazard ground motion. All right? And again, remember, the uniform hazard ground motion is just what gets 1 point interpolated off of the hazard curves. All right? So for these two locations, San Francisco, risk targeted, we ended up at 1.4. We started with a uniform hazard ground motion of 1.3, and the risk coefficient is 1.7. So risk targeted ground motions are a little bit bigger than uniform hazard ground motions for the San Francisco location. And then in contrast for Memphis, the risk targeted ground motion is about 1 G, and the uniform hazard is 1.2. So 0.82 is the drop in ground motion if you go to a risk-targeted approach versus uniform hazard approach. So I'll show some of these risk coefficients for other locations in a second, but want to mention one thing that comes up later too, that so essentially these risk coefficients, they're kind of a parameterization of the shapes of hazard curves. Again, for these two locations, we had different shapes of hazard curves, and that ends up getting reflected in the risk coefficient. The risk coefficient here being less than 1 for Memphis and a little bit more than 1 for San Francisco. If the shapes of the hazard curves in the two locations had been the same, they would have the same risk coefficient. Okay, so this is just a map for the Deterministic US of these risk coefficients, and I'll actually quickly go and show you just the places where the risk coefficient, that is the ratio of risk targeted to uniform hazard ground motions, is less than 0.5, or 0.85, sorry. So this is where going to a risk targeted ground motion approach reduces what you would do compared to our old 2% and 50 uniform hazard approach. It reduces it by more than 15%. And essentially it's around Memphis, or around the New Madrid seismic zone, around Charleston, South Carolina, and a little bit along the coast of Oregon and Washington. Right? And then a few other places around Salt Lake City, a few other places where the hazard might be pretty low to begin with. And then this is showing, and you might not see any places on, well, you can see a few probably, places where the risk coefficient is greater than 1.15. So where a risk-targeted approach increases the ground motion relative to using uniform hazard ground motions by more than 15%. And the main place is Sacramento. So this brings things up by about 15% or so in Sacramento. This location is a place where it's low hazard that becomes a little bit higher because of an interesting shape of hazard curves there. Okay, so to summarize this part, probabilistic ground motions now specified in ASC 710 site-specific procedure, they're risk-targeted ground motions. These ground motions are calculated from ground motion hazard curves from the USGS for the purposes of the MC-SABAR maps. We need a building fragility curve, and that was defined by Project 07 based on, again, work that was done for FEMA P695. And then a risk target, and that was defined by Project 07. And I'll go ahead and, I'm remembering, so I'll just mention this now. We saw this Memphis and San Francisco examples, and we saw, hey, the risks that we were getting before we went to risk target was about 1%, but it was different in the two locations. And that was pretty much true across a lot of the US, especially a lot of the Western US, that what we were doing before was around 1% in 50-year risk. And so that's why it became really the risk target. We weren't trying to change things drastically from before. We're just trying to even up the risk essentially across the country geographically. Right? But that's why we use the 1% in 50-year risk as a target. All right, and so risk coefficients are this ratio of the risk-targeted ground motions to uniform hazard ground motions. And I mentioned that because if you are looking at the site-specific procedure of ASC 710, you'll find risk coefficient maps in there. And they're in there for kind of combination with site-specific uniform hazard ground motions for an approximate way of getting at risk-targeted ground motions. Right? So those maps in there essentially allow you to do your own hazard analysis, but when it comes to doing the risk-targeted ground motion calculation, you can kind of pull a coefficient off the maps that is based on the USGS hazard curve. So that's method one in the site-specific procedure. But for these maps, we calculate risk-targeted ground motions directly. It's not a process of calculating a uniform hazard and then figuring out a correction factor. You calculate risk-targeted ground motions directly. This risk coefficient just comes into play because people want to know how they compare to uniform hazard ground motions. And then if they're not going to do their own risk-targeted ground motion calculation, they do want an approximate way of going from uniform hazard to risk-targeted. Okay, so we've gotten through the probabilistic risk-targeted ground motion part now. For the MC-SABAR ground motion maps, there's again those deterministic caps that factor in. All right, so I'll talk about those pretty briefly. All right, so again, in the site-specific procedure of ASC 710 and 2009 NEHR provisions, you can find written there, it defines the deterministic ground motions as 84th percentile ground motions in the direction of maximum horizontal response, max direction. This ... is probably where it says that, deterministic ground, if you look at characteristic earthquakes around your site and you choose the characteristic earthquake that gives you the biggest 84th percentile ground motion at your location. And then there's a floor essentially to these deterministic ground motions. All right, so kind of summarizing equations, since there's a floor, deterministic ground motion is kind of the bigger of an 84th percentile ground motion, and then some value that's a function of FA and FV, the site coefficients. Right? For our maps, we're doing them for site class, well, site class B, the BC boundary, which is something that Yusuf talked about as being kind of rectified in the current code. So essentially, we're using a floor of 1.5 G for 0.2 second and 0.6 G for 1 second. Right? These are maximum direction ground motions, like the probabilistic ground motions are. All right, and then what the USGS, out of the USGS hazard model, what we actually provided to Project 07 is we actually provided median 50th percentile ground motions, part of that just for simplicity and for consistency with what was done in a previous cycle. And then again, we couldn't give max direction ground motions directly, so we gave what we could, geometric mean ground motion maps. But this is a map showing, for each site, this is telling you what the biggest ground motion is for all the characteristic earthquakes biggest median, geomean, ground motion for all the characteristic earthquakes that could affect your site. And then Project 07 decided, okay, we got median ground motions from USGS. We're going to use a factor of 1.8 to get 84th percentile ground motions. 1.8 corresponds to a GMPE logarithmic standard deviation of about 0.6, which is reasonable. Then for the max direction conversion, again, we use the factors of 1.1 for 0.2 second and 1.3 for 1 second. So at the end of the day, as I mentioned, the deterministic ground motions, you can calculate them there essentially the max of 1.1 times 1.8 times the median ground motion from the USGS for 0.2 second, but no lower than 1.5 G. And then similarly for 1 second spectral acceleration, you just have a 1.3 factor for the maximum direction conversion. Still the 1.8 to go from 50th percentile to 84th, and then a floor of 0.6 G. And these floor values they essentially come from equivalents of the old UBC zone 4. Okay, so now we have the probabilistic risk targeted part, the deterministic part, and the minimum of those two is what becomes the MC sub R ground motion map that we see in the 2012 IBC. Okay, so we've gone over kind of the derivation of the MC sub R maps. Again, that's more complicated than it used to be, and it gets, but we're trying to create web tools that make it easier to get at these values and also to help you with site-specific assessments. So the first web tool that I'll talk about here, is essentially the replacement. Some of you may have used, some of you may be using this already, but some of you may have used the Java ground motion parameter calculator that you download from the USGS, and you can get at ground motion values from the 2009 IBC or previous editions. Now we're just moving to just a web-based version of that, just a web page, nothing you have to download. And it includes the 2012 IBC, also ASC 7, 2010, the 2009 year provisions. Those will all give you kind of the same final values, but just with a little bit different formatting. And now in this tool, we've also gone back and included the old 2009 IBC and the 2006 IBC in that as well. So there were some people that were starting to use this even before the conversion over to 2012 IBC. What we haven't done yet is sort of the old 2000, 2003 international building codes. We'll put those in here, and then we'll retire the Java ground motion parameter calculator. All right, so an example of using this real quick, so use the 2009 NEHR, because again, we'll give you equivalent values to the 2012 International Building Code, but we'll give you a little bit more information, as we'll see. So you can select that design document, optional title, you select your site soil classification, here D is an example, the risk category, what used to be occupancy category, and then you enter a latitude and longitude. It'll map that latitude and longitude for you so you can kind of visually check that. So this is what you do if you want to do just one particular location. If you have a list of locations that you want values for, there's a batch mode, this tab here, that you can run and do. I think it tries to limit you to about 50, it probably works for 100 sites at a time. So you can get the results for a large number of sites at a time without having to do them manually. Okay. And then when you do push compute values, it returns a few reports. So it returns first a summary report that kind of echoes your input, and then gives you the fundamental values you want, the SS and S1 values, the 0.2 second and 1 second MC sub R values. Then those values after you've modified for site class, in this example, site class D, and then the final design values that are 2/3 the site modified values. And it shows you the MC sub R spectrum and the design spectrum. They're just cut off here. And then one thing that some people are missing, so we're trying to make this a little more obvious, that there's a view detailed report option here. You can go into it, and it essentially then it gives you it kind of mimics what you would do by hand going through whatever document, in this case the 2009 NEHR provisions. All right? So it goes through all the sections and it provides the numbers and sort of shows you the calculations. So this is showing you, for example, pulling off the in the NEHR provisions, you pull off a uniform hazard value from one particular map, in this case for short period. And then later on, it shows you how you take that uniform hazard value, you multiply by a risk coefficient in the NEHR provisions to get a probabilistic ground motion, tells you what the deterministic ground motion is, and then tells you what the final MC sub R ground motion is. So you can see the pieces, the probabilistic part, the deterministic part, and then the probabilistic part, the risk targeted part that we calculate directly, is actually shown to you in a dissected way, where it shows you a uniform hazard ground motion and a ratio of risk targeted to uniform hazard. All right. And it gives you a little bit more detail on how the site factors were calculated as well. Okay, so this is another different tool that probably is more useful for people doing site-specific assessments. So it essentially contains all the hazard curves from, right now, just from the 2008 USGS hazard model. All right? So similar to the other one, you can put in a particular location that it will show you on the map. And then it gives you back all the hazard curves that the USGS has calculated for that particular location. So probably too hard to see down here, but so, for the building code maps, we've provided 0.2 second spectral acceleration, 1 second spectral acceleration, also PGA, just at the BC boundary site class. All right, so those are the maps, but we've actually calculated hazard curves for a bunch of different periods. These are PGA 0.1, 0.2, 0.3, 0.5, 0.75, up to 5 seconds. And then also on this axis, we actually calculated using the VS30 parameter in the NGA West 1 relation. So this is something that maybe isn't necessarily available in the East, but we have hazard curves for site class B, the BC boundary, C, D, CD boundary D, and DE boundary. All right, so you can get at these hazard curves through this tool, and ultimately we'll add the new hazard curves to this. And then one thing that we've finally been able to do, we've gotten the web development time that we've needed by paying for it. You can't get what you need for free. So we have a tool now where you can input a hazard curve, so your own site-specific hazard curve, or one of the hazard curves from the previous tool if you'd like, and it will return what the risk-targeted ground motion is. It does this iterative integration of that hazard curve with the fragility curve that's defined by the site-specific procedure. All right? So yeah, you just put in spectral acceleration values of your hazard curve, the annual frequency of exceedance values of your hazard curve. The graphics here are cut off, but actually for anyone who's looking at their notebook, we didn't have this ready by the time I submit those slides, so we popped in there just a figure from MATLAB that kind of illustrates the risk-targeted calculation and the iterations that are done, and this tool will show you those as well, so you can kind of look at the specifics a little bit more. But most importantly for most people, it gives you back the risk-targeted ground motion value. This isn't complete yet. We got to do some QA, and also we've gotten a little bit of feedback so far, and we're gonna make it easier to put in multiple hazard curves at the same time, for example. Probably not something that we're gonna be able to get back to until, or be done with at least until January, but that's the plan. Okay, so now pretty quickly, we're 5 minutes away from lunch, and this will go pretty quick, so it'll be about right. Impact of change from NGA West 1 to NGA West 2 on MC sub R ground motions and relative to impact of other modeling changes. Okay, so before I actually show a figure, okay, so remember MC sub R ground motions, they're the minimum of probabilistic and deterministic ground motions. Probabilistic ground motions, now they're risk-targeted ground motions, and you can dissect those into a uniform hazard ground motion times a risk coefficient. And so what I'm going to show is actually, we're just going to focus on the impacts on the uniform hazard ground motion part, which you already saw some of in Mark's, but I'll show that again just to reinforce that. And then the impacts of changing from NGA West 2 or from West 1 to NGA West 2 on risk coefficients. So I'm not showing impacts on deterministic ground motions here, in part because we're sorting those out still, and the other part is that you're going to see other talks in the afternoon where they're focused a little bit more on the impact on deterministic ground motions. So you'll get that from others. All right, and then I'm going to show just the impacts of changes, just only changing from NGA West 1 to NGA West 2, leaving everything else in the model the same, only changing that. And then relative to the changes from the 2009 NEHRP provisions in the MC sub, or the uniform hazard or risk coefficients that are in there to what's been calculated for a proposal for the 2015 NEHRP provisions. All right, so these changes will include, all the changes in the USGS hazard model, not just NGA West 2 with the source modeling, other ground motion prediction equations. This also is going to include the change of beta, that fragility curve slope or standard deviation that I mentioned, from 0.8, which was what we used in the last set of maps, to 0.6, which is what's specified in the site-specific procedure. And then also a slight change in max direction vectors, which I'll go over now. All right, so another product essentially that came out of the NGA West 2 project was this report by Shahi and Baker, where they looked at the ratio of max direction spectral accelerations to the new parameter that's being used for NGA West 2, that ROT-D50. All right? So they looked at that ratio as a function of period, and they're getting this curve. And you can see that roughly at 0.2 seconds, it's around 1.2 is the maximum direction factor, and at 1 second, the factor is about 1.25. Right? Just put that in perspective. Shahi and Baker, they also looked at, well, all right, this is because now we have ROT-D50 as our new ground motion parameter from NGA West 2. Before we were using GM ROT I50 with the same approach they're using, which includes all the data from the NGA West data, or NGA West 2 database, and then also I think they did a good job of how they processed all that data and coming up with these factors. So they looked at their answer for the old GM ROT I50, this solid black line, compared to some other studies that some of this I think really came out after the last building code cycle, or at least pretty concurrently with it. These other lines here, and then compared to what we're using for the 2012 IBC values, the max, that 1.1 second max direction factor at 0.2 second that I mentioned, and the 1.3 seconds. So what you can see a couple things here. Like one, yeah, it's probably pretty clear that we should probably, at 0.2 second, we should bump up to about a 1.2 factor on max direction based on this. The 1.3 is not all that different than what we're getting out of Shahi and Baker, but again, this approach is specific to the ground motion intensity measure that's used by NGA West 2, and that doesn't make too much of a difference until you get out to longer periods. You can see here it's at 1.3 second, and over here in this plot it's above 1.35, so there's a little bit of difference in these ratios when you look at this ground motion parameter. And I'll say the other reason I'm transitioning to this is that I forgot to mention in an earlier slide, right now there's a proposal moving forward in the building code update cycle to not create maps for other periods besides 0.1, 0.2, and 1 second, but at least to refer to values that will be up on the USGS website, MC(R) ground motion values for periods other than 0.2 and 1 second. And for that, we're going to need max direction factors for periods other than 0.2 and 1 second. And they've done a pretty complete job here at quantifying those factors. Okay, so finally the couple maps I wanted to show. On the left here is the ratio of the uniform hazard ground motions, the 2% and 50-year ground motions, for NGA West 2, using NGA West 2 divided by using NGA West 1, everything else the same. And then on the right, essentially the ratio of the uniform hazard ground motion from the 2009 NEHR provisions, and then what's being proposed right now for 2015, which includes the ground motion model changes, the source model changes like Mark talked about, and also this change in max direction factor for 1 second going from 1.3 to 1.25, so decreasing that factor a little bit. And you can see here the NGA West 2 by itself, it doesn't have, has around big faults that might have, a 10, 15, maybe in some places 20% increase there. Relative to the changes in uniform hazard ground motion that you're seeing from all the impacts, these three and the source models included, here you're starting to see places that are going down, by more than 20% in some places and going up by more than 20% in others. And then you can look at this in terms of risk coefficients. All right? So, and remember risk coefficients in kind of a quantification of a shape of a hazard curve. So here on the left, when we're changing from NGA West 1 to NGA West 2, this is basically showing, well, how much has NGA West 2 changed shapes of hazard curves? And it really hasn't changed it much. These are changed in risk coefficients by maybe 5% at most. So there's not much of an effect on the shape of hazard curves. Although it's interesting, there most places it's bringing the risk coefficient down a little bit. So there is something systematic that I'm not sure about right now. But again, small changes, so not too impactful. And then even when you change the other things, again, the source models, and now change beta from 0.8 to 0.6, even then, you're getting changes here that are plus or minus 10% more minus, and at most like a 15% change. So even changing the source models, changing the beta, changing the ground motion prediction equations, it's not changing these risk coefficients or the shapes of hazard curves all that much. Okay, and then these are similar plots for 0.2 second. I'll just go over these quickly. Again, effect of NGA West 2, changing that only here on the left. It increases things a little bit along San Andreas. Now, the max direction factor going from 1.1 to 1.2, that's straight off about a 10% increase, but you got source modeling effects in here as well. So there's more of a change here, including all these effects. And then same thing for the risk coefficient for 0.2 second. Pretty small change here, just when you change NGA to NGA West 2, a little bit bigger, but still pretty small change when you make these other source modeling and beta changes. Okay, so to summarize, drill this in, MC sub R ground motions in the 2012 IBC, they're minimum of risk targeted ground motions and deterministic ground motions. These risk targeted ground motions are a little bit more complicated to compute, but these new USGS web tools make it easier to obtain them, and also the one that we're going to introduce in January means you can do the risk targeted ground motion calculation with your own hazard curve. The impact of NGA West 2 on the uniform hazard ground motions, and Mark showed some of this, it's noticeable, but I guess I characterize it as small compared to all the modeling changes, like the other updates in the USGS hazard model, changing beta, changing the max direction factor. There are cases where the change in NGA West 2 and then these other things all kind of offset each other. So in the end, you don't get much of a change at all, even if you get some change from the pieces. So that's a bit contrary to this conclusion, but in general, I thought this was fair to say. And then the last one is, the impact of NGA West 2 on the risk coefficients is really pretty negligible, plus or minus 5%. And in fact, the impact of all the modeling changes on the risk coefficient isn't that great. Those risk coefficients are pretty robust. They just depend on shapes of hazard curves. So again, unless you do something pretty drastic, you're not going to see an impact. Shapes of hazard curves are quite different in the West and the East, but different modeling of the West, different modeling in the East to date hasn't changed those a lot. And that's it. If anyone, especially for that tool that I wasn't able to give the website, if this is my email if you want to know when that comes out and where to find it. All right, thank you.